So we've talked about how the Laplace transform could help us solve differential equations, and we've used some powerful theorems in order to compute the Laplace transform and inverse Laplace transform. In particular, the linearity theorem is important. And what we'll do here is talk about some other theorem, the first translation theorem, which deals with translation in S space, in the space of that you're at after you apply the Laplace transform. So here it is. If the Laplace transform of a function lowercase f of t is equal to capital F of s exists for s is greater than c and a is any real number, then the Laplace transform of the exponential e to the at, where of course a is a constant, times lowercase f is equal to the Laplace transform of f with s translated to s minus a. Okay, so wherever you see s, you substitute s minus a. And so you get capital F s minus a, where of course capital Fs is just the Laplace transform of f. So that's the effect. So if you translate, we could also, and of course this is true for s is greater than a plus c, we could also frame this in inverse form, okay? And what that tells us is that if you translate the transformed function, so capital F, a units to the right, okay? If you translate that a units to the right and you take the inverse Laplace transform, what you end up getting is the function, which is the inverse of the Laplace transform without any translation, times e to the at, okay? So that's the effect of multiplying by e to the at of a function f and applying the Laplace transform. It translates the transformed function a units to the right. So let's look at some examples. We have here, we want to compute the Laplace transform of this, and for b, this. Okay, for a, we see we have that e to the 5t. Automatically, we could identify a here in the theorem as 5, in our function as t cubed, okay? And so using this form, we have then that this is equal to the Laplace transform of the function, where we're going to substitute, instead of s minus 5, okay? And we know the Laplace transform of t cubed, it's 3 factorial over s to the 4th. That was something that we had discussed earlier, and it's a basic function which we use its Laplace transform to take Laplace transform of more complicated functions. And so we're going to substitute s minus 5 wherever we see a s there, and this is what we get. What about b? Well, here a is equal to negative 2. Again, doing something similar there, but being cognizant that, you know, we have a s minus negative 2 there, okay? And so that's s plus 2, right? And so the Laplace transform of cosine 4t, again, that's a basic one, so we know it. And we then just substitute s plus 2 wherever we see an s, and we arrive at this Laplace transform. We could also look at examples in inverse form. So here we have that we want to compute this for a. So what are we going to do when we see something like this? Well, the first thing you're going to do is partial fraction decomposition, okay? We then set this equal to this expression here, and we solve for a and b. I have videos on partial fraction decomposition in the Calc 2 series. You're welcome to watch that to understand more in depth how this is done. And so we have that the inverse Laplace transform of this is equal to this expression there. And by linearity, we have that. And this is a basic inverse Laplace transform. We know that. It's just e to the 3t. But what about this? Okay, what about this? Well, this is S space. and we're translated 3 units to the right, okay, s minus 3. And so what we'll do is say that this is just 1 over s squared, which we know the Laplace transform, the inverse Laplace transform of, where s should be substituted to s minus 3. Here it is in this form, and so we just apply that, and we'll get that our final inverse Laplace transform is this over here, which was straightforward, and this over here, which is 11e3t times t, okay, because the inverse Laplace transform of 1 over s squared is just t, and we have this e to the 3t due to the translation. Now, what about b? We want to take the inverse Laplace transform of this. Well, we could try, say, to factor this, but this is actually not factorable, all right? So, because we've been talking about translations in S space, a good strategy is to complete the square, okay? And completing the square is the objective is to get a perfect square. And so we could see that we, ignoring this and just seeing that if we add and subtract 4, which is just 0, what we could do is take this, okay, this is why we added and subtracted 4, and turn it into this. We get that perfect square. And negative 4 plus 6 is just plus 2, and so we're left with that right there, okay? And because we got a s plus 2, we want to cast everything with s here as having a s plus 2. So we do that by just this basic arithmetic, right? Add and subtract 1 just to get a s plus 2 there, okay? And so we have that the numerator, okay, the numerator over here is equal to this. Okay, now we have our s plus 2 in the numerator and in the denominator, okay? And so applying that, we get this expression, okay? And now just by simple rules of a plus b over c is equal to a over c plus b over c, we get this, and then we apply linearity and we get that. And now because we have s plus 2, we've translated. What we're going to do is use the first translation theorem, okay? This is just s space translated 2 units to the left, or substituting s with s plus 2. And now this, we do know the inverse Laplace transform of, okay? These two, both of these we know the inverse Laplace transform of. That's from the basic table, but we do need a root 2 there, okay? Because if you look at the table, it's framed as k over s squared plus k squared, okay? But this gives us a sign root 2, okay? And so that's where the root 2 comes. We actually multiplied by 1 and then left a root 2 here and a root 2 up there. And this 2/3 just came along. And this is the inverse Laplace transform of cosine root 2, but we get translations in both of these, okay? And so there goes your factors of e to the minus 2 due to the translation of 2 units to the left. So let's use our knowledge of the first translation theorem to compute a solution to this initial value problem, okay? What do? We apply the Laplace transform to the differential equations, and here we're going faster because we already discussed this, okay, in depth. So we apply the Laplace transform to both sides. We end up with this expression with these initial conditions. We make the substitution y0 equals 2 and y prime of 0 equals 17. We also make that here, and we end up with and this here is the Laplace transform of the right-hand side, the non-homogeneous term. And we end up with this expression here. We could factor s squared minus 6s plus 9, okay? It's a perfect square, and we get this over here. And we end up with this expression. Now, in general, you would have to combine these and then do a partial fraction decomposition, okay? But we already did a partial fraction decomposition of this guy, and this guy already has just a constant on it. So the partial fraction decomposition, we did that in a previous example up here, over here, okay? And so we have the partial fraction decomposition. All right, so we solved for our y of s algebraically. That's what the Laplace transform allows us to do. In S space, we substituted a differential equation for an algebraic equation. We got the solution to the algebraic equation, and now we are going to apply the inverse Laplace transform. We used partial fraction so that applying the inverse Laplace transform would be easy. You know, technically this is an algebraic solution. We could have combined them even. So applying the inverse Laplace transform on each of these terms, and noting the translations of 3 units to the right, okay, these substitutions, we then get, and this here is a 3, even though that's not clear. There, that's actually 3, okay? And so we get this at the end when we take the inverse Laplace transform and use the first translation theorem. Let's look at one more example for solving differential equations. It's pretty similar. We apply the Laplace transform. We end up with this expression here. We solve for ys, and now using partial fraction decomposition, we could break this up into this sum here, okay? And we've already worked with this previously. That was in this step over here, okay? So we found the inverse Laplace transform of that expression, so we don't have to do it again. And so what we're going to do is apply the inverse Laplace transform now to get y of t, the solution, okay? And we end up with this solution, okay? This is just coming from our previous work, okay? And these are straightforward inverse Laplace transforms, okay, which result in these terms. But now these, which comes from this, was more involved and required the first translation theorem to make it much easier.